Welcome! In this section, we'll use next sentence prediction as a practical way to understand how modern language models work and how that shows up in interviews. It's part of a career-focused guide covering LLM roles, AI engineering interview prep, and core NLP fundamentals. We'll start with BERT, then connect those ideas to what comes beyond it in today's model landscape. Here's the roadmap for this talk. We'll start with what next sentence prediction, or NSP, actually is and how it was used in training. Then, we'll look at why it mattered and what problems it was meant to solve. After that, we'll cover the debate around NSP, including RoBERTa and Albert. Finally, we'll bring it to today's systems and end with practical career takeaways, projects, and interview-ready talking points. Next sentence prediction, or NSP, is a binary sentence pair task used during BERT pre-training. The model sees two sentences and predicts whether the second one truly follows the first or is just a random sentence. Training is split evenly between real next sentences and random pairs. It uses the CLS token as the sequence level representation, and it's trained jointly with masked language modeling, so the model learns both sentence relationships and word-level context. This slide shows the setup for next sentence prediction, or NSP. We feed in a pair of sentences, take BERT's pooled representation, typically the CLS output, and pass it to a binary classifier. That classifier predicts whether the second sentence truly follows the first. The key idea is that NSP adds sequence-level supervision, while masked language modeling works at the token level. That distinction comes up often in interviews because it highlights what BERT is learning beyond individual words. Next sentence prediction was introduced to help BERT learn relationships between pairs of text segments. That matters for downstream tasks like question answering, where a question must connect to a passage, natural language inference, which tests entailment between a premise and hypothesis, retrieval and ranking, where the model judges whether spans belong together, and coherence, such as ordering or linking relevant text segments. The key idea is sentence pair reasoning, not text generation. One interview point that really stands out is this: next sentence prediction is not a generation task. It teaches a model to decide whether two spans of text belong together, which makes it much more relevant to retrieval, entailment, and ranking. So in interviews, especially for LLM application, search, or agent roles, frame NSP as a matching or relevance signal, not as a text generation capability. This slide is about the pre-training objective landscape. Different objectives teach a model in different ways, because each one provides its own kind of supervision signal. Some are better for learning broad language patterns, while others encourage reasoning, alignment, or prediction under specific constraints. The key point is that there is no single best objective in every case. Strong candidates stand out by understanding those trade-offs and knowing when each objective makes sense. RoBERTa revisited BERT's training setup and made one especially important change. It removed next sentence prediction, or NSP. Along with that, it trained longer, on more data, and with longer input sequences. Under those stronger training conditions, performance actually improved without NSP. The bigger lesson is useful beyond this model. Understanding where a method falls short can be just as valuable as understanding what it was originally designed to do. Albert refined BERT's next sentence prediction by replacing it with sentence order prediction, or SOP. Instead of asking whether two sentences simply belong together, SOP asks if they're in the right order or have been swapped. That creates harder negative examples and better tests discourse coherence. The result was more consistent gains on multi-sentence tasks, showing that the original goal still mattered. Albert just found a better way to train it. This timeline shows how training objectives evolved. In 2018, BERT introduced masked language modeling and next sentence prediction for sentence pair tasks. In 2019, RoBERTa showed that removing NSP and training longer could beat BERT. Albert then replaced NSP with sentence order prediction, a tougher coherence signal. Sentence-BERT followed with a Siamese setup for efficient sentence embeddings. Today, production systems rely heavily on embeddings, re-rankers, and retrieval. In today's LLM landscape, next sentence prediction is mostly associated with encoder models like BERT, where it supported tasks such as classification, natural language inference, retrieval, re-ranking, sentence matching, and other coherence-sensitive applications. By contrast, decoder models like GPT are built for free-form generation, chat, coding, and agent workflows. So for modern decoder-only systems, NSP is best framed as historical context, rather than a core method used in practice. Sentence-BERT solved a major practical limitation of vanilla BERT. With standard BERT, you have to feed both sentences together, which makes large-scale similarity search far too slow. Sentence-BERT uses Siamese and triplet network training to create independent sentence embeddings, so you can compare them efficiently with cosine similarity. The result is a huge speedup. 10,000 by 10,000, similarity search drops from about 65 hours to just 5 seconds. A key skill in retrieval and ranking work is knowing when to use a cross-encoder versus an embedding model. Embedding models are great for fast, scalable retrieval because they let you compare vectors efficiently across large document sets. Cross-encoders are slower, but usually more accurate because they score a query and document together. In practice, strong candidates know how to combine both, embeddings for recall and cross-encoders for precise re-ranking. Here's a quick model family cheat sheet. BERT uses masked language modeling plus next sentence prediction, so it's strong for classification, natural language inference, and question answering, but not for open-ended generation. RoBERTa is similar, optimized for classification and retrieval. Sentence-BERT is built for semantic similarity and search. GPT-style decoders are best for generation and chat. And Albert, with sentence order prediction, is useful when multi-sentence coherence matters. There are 3 skills employers really look for here. First, understanding the trade-offs between MLM, NSP, SOP, and next token prediction, what signal each objective teaches, and when it actually makes sense. Second, knowing model task fit, when to use an encoder, a decoder, or a sentence transformer. And third, hands-on tooling, being able to prototype sentence pair tasks in Hugging Face using BERT NSP classes, embeddings, and simple evaluation pipelines. A strong portfolio project here is to compare sentence pair approaches side by side, a cross-encoder BERT model versus sentence-BERT embeddings. Define a clear benchmark around similarity, duplicate detection, or re-ranking. Then document not just results, but the design trade-offs, accuracy, latency, and scalability. In the write-up, show objective thinking. And if you mention NSP, use it as historical context for why sentence-level supervision became important, not as the core of a modern system. Here's the model answer. In BERT, next sentence prediction, or NSP, was a pre-training task that asked whether one sentence truly followed another. The goal was to help with inter-sentence reasoning in tasks like natural language inference and question answering. Later, RoBERTa showed you could remove NSP and still do better with stronger training, while Albert replaced it with sentence order prediction. Today, its closest descendants are sentence pair models, re-rankers, and embedding systems. What interviewers are really testing here is whether you can reason at 3 levels. First, objective design. What supervision signal does next sentence prediction actually provide? Second, model behavior. How does that training objective influence what the model learns? And third, product architecture. Which downstream system components actually benefit from that capability? Strong candidates don't just define NSP. They connect the objective, the learned behavior, and the product implications. When you're planning your learning, be strategic about where your time goes. Know NSP well enough to define it, explain why it was introduced in BERT, and why later work moved away from it. But spend most of your effort on the areas that matter more today: transformer architectures, embedding and retrieval pipelines, sentence paired datasets and evaluation, latency versus quality trade-offs, and being fluent with Hugging Face tools. To wrap up, NSP is really about sentence pair classification. It taught models to capture relationships between sentences through the CLS representation, not to generate text. The idea didn't disappear. It evolved. RoBERTa dropped it. Albert refined it, showing that objective design matters more than any one method. And its impact is still practical today in retrieval, reranking, semantic search, and coherence tasks. It's a great example of how training objectives shape model behavior and system design.